In this video, we're going to talk about Bayesian optimization. This comes off the back of a comment from Scola Lewis who asked, could you show a 3D function example, e.g. a 2D input space? So in order to do this, I thought that we'll take an optimization function that you can click on here, the test functions of optimization, and we'll just pick one that looks a bit interesting. So I've chosen the Stablinski-Tang function. So this function has 4 local minima points that we can choose for the minimization problem, but it does have one global minima, which I've shown here. And you can go on Wikipedia to look at other examples, but I chose this one because this one looked a bit interesting. So I will show you the contour plot in a second, where you can see the 4 local minima. But in this particular case, what I want to impress on you is just how the setup looks like. It looks very similar to before, and also some of the other auxiliary convergence plots and whatnot that you can get from this kind of problem, more specifically the partial dependency plots. I'll show you how maybe you can draw them yourself, and also of course how you can use the scikit-optimize function to do this for you rather than building it by hand. But as always, we're going to show you how you can do it manually first before using the actual using an inbuilt library to do this. So we'll start off by showing you, we'll start off for simplicity's sake to show you what the objective function looks like. So this is just the objective function that I've represented in Python code, and I've also have a one-dimensional version of this. So this is one way of how you can do a partial dependency plot. So more or less what I'm doing is, because this function is somewhat symmetrical, right? It doesn't really matter which order you put in the parameters. In this case, I just want to show the partial dependency over one particular axis. So for every single point here, we're just going to just take the mean and slice it, and I'll show you what that looks like in a second. If we wanted to do this using the scikit-optimize library, the setup would look like this. We're not going to run it here. We'll run it a bit later. And what you do is, again, you put in the bounds. In this particular case, if you go on Wikipedia, you'll know that the bounds are -5 to 5 for all dimensions. And but before we even run this, let's just have a look at the contour plot to know what we're dealing with. So in this particular plot, you can see that there are some local minima points, right? And what we really want to do is we want to get to the point that is -2.9 and -2.9. So it will be in this particular region. Notice that if you just do a naive stochastic gradient descent, you could end up in a local minima point, which is here or here, rather than over here. All right, so let's have a look at what it would look like if we do exactly what we did before. So firstly, let's go ahead and just apply our Gaussian regressor. All right. This time, again, we just need to take care of how we build these. So in this particular case, what I've done is I've sampled from the x and y axes, which is how I'm labeling the 2 axes. And I've I stacked them together, right, so that they are pairs of points. And then I've fit them against y. So y would be my objective, which I've defined here. So I've just put in these 2 samples using this numpy vectorize function to calculate what the y's are. So I've used that to fit our Gaussian regressor. Right, so right now all of this looks very much the same as before. Okay, so how do we visualize what this looks like? So again, we can turn to our contour plots to have a look. So here we have our predictions, which I've called y. I should have probably called it y pred or something else. But you can see that we do exactly the same thing. We stack the points across this space that we're doing this contour plot. And we're just going to plot the contours. So you can see that in this particular case, based on these random 5 points, this is the contour plot that we get, the surface estimated by our Gaussian process. All right. So again, we can start to see that we're getting somewhere. We have our we have the mean for our Gaussian process, and we can of course also return the standard deviation. And if we change this to our standard deviation, so where we want to get the lower confidence bound, we can do that as well here. As you can see, y0 minus y1. So I've returned standard deviation here to the y object. So the first element, so y0 would be the mean of the prediction, and y1 will be the standard deviation. So this will be the one standard deviation confidence bound, so the lower confidence bound, and this is a corresponding contour plot. Now this is a bit hard to visualize implicitly because it doesn't really tell us anything. So what you might want to do is you might want to plot a one-dimensional version of this. There are many ways of doing this, and there are assumptions that you apply. So if we just assume that all the points are uniformly distributed, we can just fix one particular dimension and just sample everything along that dimension. So we can do that here. So in this particular case, I've used the one-dimensional objective, and I've just sampled across this whole line space here, right, which is at x. And this allows us to show you, if we just cut across like that, this is what the curves look like. So in blue, we have the ground truth for this partial dependency plot, and we have in red the 5 sampled points, right? And then over here, we can see what the Gaussian process line looks like. Keep in mind, why these red points don't intersect is because this is the partial dependency, right? If we recall in the previous video about the Gaussian process, when we do have this red line, because we didn't add any noise to our Gaussian process, the dots would exactly line up on this red line. In this case, it's not true because it's a partial dependency plot. I'll show you later on in the video, probably towards the end, what happens when we change our sampling, and you can see how these lines change as well. All right. So we can do very much the same thing like as before. We can use the upper confidence bound for the exploitation kind of approach, or we can use expected improvement to also fill it in. So you can see that in this kind of we can again plot like confidence bounds over partial dependency plots. It doesn't really make sense. And I'll leave that as an exercise for you to think about why this might not be precisely correct and why it looks so off, right? It has something to do with how you average out everything. But rather than go through that in too much detail, let's have a look at what happens if you actually use the scikit-optimized library. So if you use the scikit-optimized library, they do have a lot of auxiliary plots and functions that are probably more useful than handcrafting it yourself. And with far less code and less error for making mistakes. I've probably made a bunch of mistakes here, and probably someone watching this video in the future will probably tell me I'm wrong, and that's okay, because this just shows you the amount of effort you need to apply, and it's not all that obvious, even from a naive standpoint of just coding this thing up, that you'll get it correct. And I'm pretty sure I've got something wrong already. Simply because when you look at this plot, it just doesn't look right. It doesn't make intuitive sense, right? Why are there the sampling plots outside of this region that's shaded? It just means that maybe my setup of the Gaussian process is already incorrect. Maybe I need to change the kernel or the parameters that are within the kernel that I've chosen, right? So these kind of hyperparameter optimization questions come into play, and all of this additional complexity just means that something is probably going to give and something is probably not working as we would like. We do sort of see, though, in this particular case, even despite that these points don't reside in this confidence bound that I've drawn, that it does follow the rough shape of the target function, which is a good thing, because it means that maybe if we did sample a few more points, we will eventually see that the values do have these kind of this kind of bimodal distribution. You can sort of see a bimodal distribution at the bottom line, right? So it's not that all hope is lost, but maybe that there is probably a formulation that shows this kind of effect much greater, in a much better way. Sorry. All right. So let's turn our attention to the scikit-optimized library, and if we just run it just the way that I had before, you can see that there's a convergence that we can see. It does apparently converge, and we'll look at some of the auxiliary plots in a second. So if we look at the auxiliary plot, you can see that it's found the ideal global optima. This looks like it's pretty close to negative 2.9, which is pretty good, where it's shown in the star. And you can see the partial dependency plots where this is an expected improvement, keep in mind. You can see that there are that kind of bimodal shape. Even though this function or this search space is supposed to be symmetrical, these two plots don't look quite the same. Now, if we increase the number of calls to 30, hoping that these plots improve a bit, you do sort of get much closer to the target function that we see, and we sort of see that kind of nice symmetrical shape that we're after. So these are just some of the things that you can do with a scikit-optimized library, and it does work quite well. I mean, you didn't have to write much code, and you do get the contour plots, you do get the partial dependency plots, which is both really, really cool. You also get a line showing where the optimal value is predicted, which is also really useful. And what's interesting in this plot is you can see that in this particular instance, how it's sampled is this point is the global minima along this axis, but it is not across this axis. So how do you choose between them? And it also shows you that partial dependency is really just a tool to help you gain your intuition. It's not necessarily you stare at it and just pick the best point. All right, so as I said, let's change some of the seeds and see what happens when we do that. So I'm going to change the seed to 4 because I think the seed 4 was actually really horrendous. Oh, I need to rerun this, of course. Yeah, so let's change the seed to 4, and you can see what a big impact it has, again, on our particular function. So when we change our seed to 4, immediately the contour plot is nowhere near where we would like. So if we look at the partial dependency plots, it just sampled everything on this side. You can sort of see that it's explored a lot down here, but it doesn't really know what's going on the left-hand side. So yeah, and this is what makes me think that I've done something wrong in my definition of the bounds, because you can see that in this particular case, this part, because it hasn't been explored, should have the biggest standard deviation, but it's not reflected here. It's probably something to do with how I've sampled or taken the median of the confidence bounds, whereas you probably want to take something else. And maybe at some stage I'll play around with this to tell you what is the correct way. But again, this is just producing a partial dependency plot. It doesn't really affect the underlying algorithm in terms of how you would sample when you plug in the equations. It's just more to help you gain intuition of how the next point might have been chosen. Of course, if you plug in the actual formula, you would see something else altogether. If you look at the convergence plots here, you'd see that it doesn't find the correct point if when we sample for 10 points, right? We know that the ideal point is around like negative 2.9, so it should be here. But when we do 30 or more points, we do see the correct one. So it does show you that if you do not have the correct sort of starting point, we can get to, I guess, less than ideal areas of the plot. So we can see that in this particular case, with the partial dependency plots along this particular dimensions, it does sort of say that the expected improvement is better on the left hand side compared with this particular axis. Yeah, so this is all that I have to show for the 2-dimension Bayesian optimization. Hopefully you found it interesting. Hopefully that you found some mistakes that I've made and you can tell me where I'm wrong, so that hopefully in the future I can do a better job. Thanks for watching.